All right, so today's lesson is looking at momentum and vectors for those who missed the live one. This one doesn't have a pool table, unfortunately, or dogs helping me with the lesson. So the thing to remember with momentum is it's a vector quantity. That means that unless it's in one dimension, like the last two lessons, where you can basically make the directions the same by making one negative, you can't simply add them the way we've done mathematically. You can't just add the magnitudes, because the directions will change what the values are. So if the objects are moving with an x and a y value, you can't just add the magnitudes. You have to actually add them as vectors. So when you get row 1 plus row 2, you can't just go mv1 plus mv2 and add it. You actually have to add the two vectors using a vector diagram. Fortunately, it's exactly the same. It's literally just adding two vectors, the same thing we've done for any other vectors. So if you've got a case where you have one ball hitting another one and them going off at different angles, the billiard ball problem, you basically have momentum of ball 1 equals momentum of ball 1 after plus momentum of ball 2 after. So you just add these two vectors and that equals the vector that was the first ball. However, one thing that's really important to consider, it is momentum that is conserved, not velocity. Velocity is not conserved because a heavier object can have more momentum even though they have less velocity. So you have to find the momentum before you create your diagram. You can't just do it with velocities. You have to do it with momentum. So step 1, find the momentums. You're adding the momentums in the vector, not the velocity vectors. So to set up the triangles, the nice thing is there's only two cases I can give you on a test. Everything else will require way too much geometry, and it's just not time. We can't do it in the time that I give you on a test to do. So there are going to be two questions. One is what we call the billiard ball, where you have one object hitting a stationary object, and then they both go at a slant. So you have one object with momentum row 1, row 2 originally is 0, and then you have row 1 prime and row 2 prime as the momentums after. And when you add this up, what it looks like is row 1 equals row 1 prime plus row 2 prime. So you'll notice these two vectors equal the same as row 1. So there's your triangle to solve for your vectors. The other one is what we call an explosion, and things in physics explode in class explode really specifically. They only explode in 2 dimensions, and they only explode into 3 pieces so that we can keep the math reasonable. By the way, this is actually how you would do it in a real explosion. If they look for where the bomb was, how big the bomb was, that sort of thing, they can actually figure that out by collecting all the pieces and figuring out this math for hundreds or thousands of things. For us, we're going to go with 3. So because it has the momentum before it exploded was 0, the total momentum after also has to be 0. So if you add row 1 prime, row 2 prime, and row 3 prime, it equals 0. And what 0 means in vectors is it literally comes right back to where you started. So again, you get a nice triangle that we can solve for sides we don't know. So to solve the collision problems, step 1, draw it. Step 2, write out conservation of momentum. Solve for any momentums you can just by multiplying the mass times the velocity for anything that was given. Draw the triangle, either the billiard ball one or the explosion one. Plug in the momentum information you've got, the angles and magnitudes you know. Then, if it's a right angle triangle, use Pythagoras and tangent to solve it. Or if it's not a right angle triangle, use cosine law and sine law to solve it. You can use components, but the trick with components is you actually have to go back and look and figure out what math operation you have to do on the components. So if you're trying to find the initial momentum, you add the other two. If you're trying to find one of the other two, you actually have to subtract one from the total. So you've got to be careful if you're using components that you're doing the right operation afterwards. That's why for these ones, I actually prefer just using cos law and sine law, because from the triangle you can tell what the value is. So, okay, it's going to look ugly, but the nice thing is you could literally just take this page, remove all the numbers, leave all the equations and just plug in any new numbers I give you, and this solution will still work exactly like this, okay? It will work every time. So let's look at this question. You've got a billiard ball moving at 2.2 meters per second with a mass of 200 grams. It strikes another ball that's at rest in a glancing collision. The first ball goes off at 30 degrees from its initial path, that's 30 degrees, with a velocity of 1.1 meter per second, and I want to know what's going to happen to the second ball, because, well, that's how we play pool. It's this ball that I care about where it's going to go. I just want to make sure this ball doesn't go into the sewer after. So, first step, write down what you know. Find the momentum for anything, find the magnitude of the momentum for anything you can. So in this case, I know V1 and V1 prime, so I can find rho 1 and rho 2 prime. I know rho 2 is 0. I want to know what is rho 2 prime. So once you've found those, write out your triangle, your conservation of law, your law of conservation. Rho total is rho total prime. Plug in the momentums. So I end up with rho 1 is rho 1 prime plus rho 2 prime. I know how to draw that. That's the billiard ball. Rho 1 equals rho 1 prime plus rho 2 prime. I know this angle is 30 degrees. I know what these values are. So the only side I don't know is this rho 2 vector, this rho 2 prime vector. So if I know two sides and the angle between them, I can use cosine law to find the magnitude, the length of this arrow, 0.27 kilogram meter per second squared. Then I can use sine law, so sine theta over rho 1 prime is sine 30 over this side that I just found. Solve for theta, so you find that that's 24 degrees, and by Z theorem, this line would be parallel to that, so this would also be 24 degrees below. So your total answer for the momentum is 0.27 kilogram meters per second, 24 degrees below its initial path. Now, the important thing is, remember, you're not done yet. You've got 8 out of the 10 marks. To get the last mark, you actually have to find the velocity by dividing it by the mass of that ball. Because if you know the momentum, you can find the velocity. And that's this solution. So for every billiard ball question, this is going to be the solution. So I really recommend, if you're doing these, look at this PowerPoint while you're doing it and just follow it exactly. It'll work every time. The only thing I can change is you might be solving for rho 1 or rho 1 prime. And I'll give you the other two sides of the triangle. That's literally the only change I can make. All right, the explosion question. So, a grenade of mass 1.2 kilograms explodes horizontally on a table. A 0.5 kilogram piece goes north at 3 meters per second. A 0.3 kilogram piece goes southwest at 45 degrees, so southwest means 45. What direction does this third piece go in? Well, by the way, one of the tricky parts about this is I'll say, what's the mass of the third piece? This is the logic one. It's one of those ones that's so easy that it messes people up. You know the total mass, you know the mass of the other two pieces, subtract them, whatever's left over is going to be the mass of that third piece. Write out everything you know. Find the momentums you can. You'll always be able to find two of the three. So I know rho 1 prime and rho 2 prime, just by multiplying the mass times the velocity. I know, write out your total momentum is total momentum prime, write out what you know. So total momentum before it explodes, 0, because it's not moving. Total momentum after is rho 1 prime plus rho 2 prime plus rho 3 prime. So again, add those up. Rho 1 prime plus rho 2 prime plus rho 3 prime must be 0. Plug in the numbers you know. 1.5, 1.3. Again, I know side-side angle. I can use cosine law to find the magnitude. I can use sine law to find the angle. Again, I can use Z theorem to find an easy angle. Remember, you always describe it from the base of that vector. And I find that the third piece goes at 1.1 kilogram meters per second, south 50 east. So this piece goes off south 50 degrees towards it goes off somewhere like this. It's not actually there. But the nice thing is you don't need to know where that is, because this triangle actually tells you what path it has to take. All right, so that's the 2 questions I can ask you. When you're doing the worksheet, just figure out which it is, look at this, just follow it, follow the procedure. It'll make more sense the more you do it, okay? So it's hard, but the nice thing, as I said about physics, is the harder it gets, the fewer questions the teacher can ask. So these are the 2 questions I can ask you. All right, see you next time.